Madeleine Udell, a professor at Cornell University and Stanford ICME alumnus, delivered a rousing closing talk during WiDS Stanford 2019. Professor Udell discusses a universal problem in data science, that of missing data, providing ideas about how to solve for missing data. I suspect that you, like me, will find Professor Udell's talk to be energizing, inspiring, and informative.
Madeleine, thanks so much for coming here and joining us and giving us the last talk of the day.
Thank you. Clicker. Okay, great. It's great to be here today. Thanks for staying. Is everyone full of energy and ready for some math? Great, because that's what we've got for you. So let me tell you the origin of my interest in this kind of mathematics. It was 2011. My advisor went on sabbatical, and so like a good PhD student, I went to do something else. And what I did is I went to the Obama campaign, which was just getting started for the 2012 election. And at that campaign, I saw the most horrible data set I had never even imagined. Okay, let me tell you what this data set looked like. So I'm showing you an example of what looks a little bit like the data sets that we had. What we had is one row for every voter in the United States, so about 300 million rows. And we had one column for everything that we knew about them. So I'm showing you 5 columns, but in fact, we had tens of thousands of columns about these people. And we knew a bunch of different kinds of things. We knew maybe their age, maybe their gender, the state that they lived in, approximately what their income was, maybe approximately what their level of education was, whether or not they had voted in any of the last elections. But a bunch of the data was missing. There were question marks all over the place, or NAs, or however you want to write them. And the data was of a variety of different types. So some of it was numerical, like age. Some of it was, in this data set, Boolean, like gender. Some variables were categorical, like state, that takes on one of 50 values. One was ordinal, level of education. And my manager said to me, well, who are these people? Can we cluster them? Can we plot them? I had no idea how to do it, right? Because it was a very large data set with different kinds of values and missing values. How do you say whether the person, two people who are the same except differing by state are more similar or more different than two people who differ only by gender? I don't know. So a lot of different challenges or goals that you might have are difficult in this setting. Right? You might want to do things like detect demographic groups, find typical responses, identify related features, or impute those pesky missing entries and figure out, for example, what's the age of that guy from California. And these are all hard because the data is so ugly. Okay, more generally, let's suppose you've got a data table. The data table has m examples, which we'll draw as rows here. These might be patients in a hospital, respondents on a survey. They could be assets in a financial model. We'll see a setting later when they're data sets in machine learning. And we've got n things that we know about these examples. These are things like values that we saw on a test, answers to questions, performance indicators for different assets. So the ith row will be the feature vector for the ith example, and the jth column will be the jth feature across all of the examples. If we're going to make progress in filling in missing data, we're going to need an assumption. And here's the assumption that I've been making successfully for several years, and I would encourage you to make this assumption too. There are really nice, beautiful theoretical reasons why I'm going to recommend this kind of model, which I would be so happy to tell you about, but I have 20 minutes. So instead I'll say, believe me that big data is low rank, and let's run with it and see what happens. Okay? So given our m by n data table, we are going to look for a skinny matrix X and a fat matrix Y so that our data table A is approximately equal to X times Y. Now that's a weird thing to say because X and Y are completely observed numeric matrices. So X times Y is a numeric matrix. And A is a data table with heterogeneous values in it and missing entries. Okay. So that's strange. But if we could figure out what squiggly equals should mean, my argument is that it would be really great. Okay? Because what it means is that we've got a compressed representation for our data table A. Okay? X and Y are smaller than A. They're numeric. And they're, in this sense, approximately equal to A. Furthermore, the rows of X and the columns of Y give you representations for every example and for every feature. We've got one row of X for every example in our data set, and one column of Y for every feature in our data set. And these are real-valued numeric vectors. We can cluster them, we can plot them, we can do anything we want with them. They're much more interpretable, they're a lot easier to work with. Okay? The third great thing about this kind of model is that the inner product, xi times yj, is approximately equal to aij. So we can do imputation. We can fill in missing values by looking at xi times yj. Okay, so once again, why would we do this? We could do it to reduce storage for our data set, speed transmission. We might be doing it to understand, visualize, or cluster our data set. We might be doing it to remove noise in our data set, looking at the entries of x times y instead of the entries of a. We might be doing it to infer missing data or to simplify data processing more generally. Okay, we'll see examples of all of these in not very many minutes. Okay, so the simplest example of a low-rank model is principal components analysis. How many of you have seen principal components analysis? Cool, everyone knows principal components analysis. That's great. Okay, so PCA is the problem of finding a low-rank model for your data set A when your data set is a fully observed numeric matrix, and when the sense in which, what do we mean by squiggly equals in the setting of PCA? What we mean is we want the x times y that's closest to A in the sense of squared error. Okay. Now, why do all of you know PCA? My claim is that it's because people have been doing it for more than 100 years. And the reason they've been doing it is because there's an easy analytical solution to this problem using the singular value decomposition, which Margot taught me many years ago. Okay, so it's easy to compute, and it's fast to compute. But for this talk, and for the horrible, messy data sets that you see every day, I want to tell you about a different way of solving this problem, which is by alternating minimization. It's a super simple idea. Fix a guess for y and minimize over x. That's a least squares problem. It's super easy, super fast. Some of you may know it by the name linear regression. Okay, fast. Now fix that guess for x and minimize over y. Once again, linear regression, least squares, fast. Keep going. Fix the guess for y, minimize over x, fix the guess for x, minimize over y. Unless you were extraordinarily unlucky, and I mean measure zero in the sense of measure theory, which scared various other panelists, but measure zero, it's not going to happen. Unless you're very unlucky, that converges to the global optimum. So it gets the same answer that you would get by the singular value decomposition, and it's much easier to generalize. Okay, so now let me tell you how to map this onto the horrible data sets that I showed you at first. And if you don't follow this math, don't worry. I'll tell it to you in code in the next slide. Okay? So there's just two changes we're going to make. The first is that instead of minimizing over every entry, we're just going to minimize over the entries that we saw. Those are the ones in some index set omega. The second change we're going to make is instead of using the squared error loss function, we're going to use some other loss function L that tells us how annoyed we are to have approximated this value A, ij, by the number xi, yj. So if you can figure out a good loss function for your setting, that tells you exactly what you mean by squiggly equals. Okay. Notice it's really important that we not be using something like subtraction when we've got aij's that could be weird kinds of values like ordinals and categoricals, because I don't know what it means to subtract California from 7. Okay, so I'm not going to tell you about which loss functions to use. Instead, I'm going to tell you that there are really great software packages that implement this framework and that have default loss functions baked in. So if you don't want to choose your loss function, you're in luck. For example, in Julia, you can fit a rank 5 generalized low-rank model in 2 lines of code. Okay? You form a GLRM on your data frame A with rank 5, and you fit it. Great. Okay, how well does it do? What can we do now that we know how to fit low-rank models? The first thing I want to tell you is how well does it do on synthetic data? If it doesn't work on synthetic data, don't try it on real data. It won't work. Okay, so this is synthetic data, but I want you to pretend like this is data from an electronic health record system in a hospital. Okay? So here's what happened is that we've got one row, every row is a patient, and each chunk of columns is a different kind of test. Okay, so the first chunk of tests are numeric, the second chunk of tests are Boolean, they have 0, 1 values, and the third chunk of tests are, have values between 1 and 7. Maybe we asked the patients what their pain was on a scale of 1 to 7. Okay. But there was a problem in our electronic health record system, and we lost the results of 2 of the kinds of tests for half of the patients. This is very embarrassing. So rather than tell the patients what happened, we're going to impute those values. Please don't try this at home. Okay, so we've removed those entries, and we're going to fit a generalized low-rank model. And what I'll show you is that you can see that the imputations look pretty good. Visually, it's hard to distinguish. And if we look at this error plot on the right, green is 0, so that's good. And so you can see most of the area is green. There's 0 error. Okay? Looks pretty good on synthetic data. Let's see what it does for some real applications. Okay. So we can do imputation. Let me tell you how to use these kinds of models to do dimensionality reduction. So I'm going to tell you about some other difficult problem. Here, it's sort of an example problem. Here, we were trying to predict which companies are going to violate US labor law. Okay, these are really bad kinds of things. It's essentially stealing money from employees, forcing them to work unpaid overtime. And these are things that employees often can't fight back against. They just don't have the institutional power to do so. Instead, we want to be able to send our law enforcement agents to the bad companies, so the companies that we think might be engaged in bad practices, so that we can stand up for the employees who can't stand up for themselves. Okay? So we want to predict who's going to violate US labor law. And one feature in this data set that I think is very interesting is zip code. Okay? But how do we use zip code in the context of an application like this? What kind of thing is zip code? I mean, there are 5 numbers there, but should we think about that as actually an integer? What kind of thing is zip code? Right? I'd say it's actually a high-dimensional categorical variable. Right? There are 33,000 or so zip codes in the United States. So my normal way of dealing with categorical variables maybe is to use a one-hot encoding. I'll create an extra dimension for every possible value of this categorical variable. But if I did that, I'm introducing 33,000 extra dimensions into my problem. I'm going to overfit. It's going to be very bad. Okay, so what do? How do I get the information out of zip code? Let me tell you about an idea that uses low-rank models. And here, we are going to use census data, which Cynthia already told us is so important. Okay? So this is how we're going to get information out of zip codes. We found another demographic data set. Here, the primary key of the data set is zip code. We've got 1 row for every zip code. And in each column, there's something that we know about the zip code. Okay? We've got a lot of columns here, 150 different columns that contain demographic information. We're going to use a generalized low-rank model to embed these zip codes into a low-dimensional space, which I want you to think of as demography space. The rank of the model is how skinny or how fat those matrices X and Y are. And that's something we can explicitly control. So we can decide if we want those zip codes to be represented by 2-dimensional vectors, 3-dimensional vectors, 10-dimensional vectors, anything we want. Okay? So let me show you what happens if I ask for a 2-dimensional vector embedding of zip codes. Here, I'm plotting a couple of points I'm not sure you can see. On the far left here is East Harlem. On the very far right is a tiny city in Kansas called McCune. In the middle, you can see some other places. You'll note that Cupertino and Sunnyvale are very close to each other in demography space. I guess people here probably know that Cupertino and Sunnyvale are very close to each other in physical space as well here in Silicon Valley. Okay? So it looks plausible. Let's see how well it does in our application. So we built 3 different sets of features to use in a supervised learning context to predict labor code violations. One was categorical, so we expanded the zip code to an extremely high-dimensional categorical variable using this one-hot encoding. Okay, so that added 33,000 dimensions to our problem. Another was to concatenate. So instead of that zip code, we replaced zip code by those 150 columns with demographic features representing zip code. Okay? That added 150 features to our model. And the third thing that we tried was to replace zip code by low-dimensional zip code features that we learned using a generalized low-rank model. Here we used rank 10. Okay? And we fit a supervised deep learning model. This was using the H2O framework. So it was the H2O deep learning framework. I want you to focus here on the way that we're doing feature engineering rather than on the supervised learning method. I just want to find better features to feed into any supervised learning method I want. Okay. And here you'll see that the generalized low-rank model features produces a model that not only has an extremely small runtime, because we didn't increase the dimensionality of our problem very much, but it also produces the lowest train error and the lowest test error. Okay? So what's interesting is even though there's less information in these 10-dimensional features than in that full demographic data set, we do better both in train error and in test error. I think that's because the low-rank model is learning what's really important from that demographic data set. And it's discarding what's noise from the demographic data set. Okay. So putting in the right information and not too much information can really speed up and improve your downstream learning procedures. Okay. I want to tell you about another application that's super weird. Okay? So when high school students in particular, undergraduates as well, when they ask me for advice about what they should do with their careers, I often say, find something you really love and automate it. So I decided to do the same to myself. I was going to work on automating machine learning. So that means when someone gives you a training data set, a set of x's and y's, and your goal is to find a function that, given the x's, predicts the y's. So maybe given everything about a company, predict how many labor code violations it will have. Given a scientist, predict if they will floss their teeth. Okay? So how do you do this, right? When you're given a new supervised learning data set, what do you do? What do you do? Yes, you try literally everything. Okay, great. So we want to do that except automatically and faster. So here's how we're going to do it using generalized low-rank models. Okay, so we're going to do it by learning across data sets as well. Okay, so given m different data sets, those are going to be the rows, and n different machine learning models, those are going to be the columns. We're going to measure the error of every model on every data set. This will take some time. Okay. We're going to form the m by n data table A. Okay, so the rows are data sets, the columns are models. We're going to find an x and a y so that x times y is approximately equal to a. Actually, this you can do just using PCA. Okay? So what does that mean? The rows of x are the data set features, and the columns of y are the model features. Okay. It's kind of weird. And the entries in x should be maybe the cross-validated error of that model on that data set. Okay? Now a new data set comes along. Okay? And I'd like to do something a little bit faster than trying everything. So I notice that this new data set puts a new row on A, and it puts a new row on X. But X only has 2 entries in it, right? I only need to estimate 2 entries in X in order to be able to multiply that X by that Y and figure out the entire row of A. Okay? So what do? I'll run a couple of models on this new data set and see how well those models perform on the data set. That fills in some entries of A. I use that to fit the corresponding row of X. That gives me the data set features. Okay? And I can use that to estimate all of the other entries. Those are the dots now. Cool. So you can think of the rows as data set metafeatures. The columns are model metafeatures. And X times Y gives you predicted model performance on these data sets. Okay. Now, this seems like a kind of crazy idea, because why should these things be low rank? But they are. Okay, so let me show you the performance of this method, which we called OBO, compared to a state-of-the-art automated machine learning system called AutoScikit-Learn. Okay, OBO is in red, essentially the same idea, but using random selections of which entries to choose instead of smarter selections is in green. And the state-of-the-art method AutoScikit-Learn is in blue. So on the y-axis, you'll see the error of the best model that system can find so far. And the x-axis is how long that code has been running. It's actually on a log scale. Okay? So you'll see that AutoScikit-Learn really can't do anything until 16 seconds have elapsed on these data sets, which are relatively small. Whereas OBO is able to find a good model that's as good as the one that AutoScikit-Learn can figure out after 16 seconds. It finds it after 1 second. Okay? So it's going 16 times faster by using the fact that it can learn across different data sets using this low-rank structure in the set of all algorithms and all data sets. Okay? So we're able to find good models substantially faster using low-rank structure. So I hope that I took some steps towards convincing you that big data is low rank. Okay? We saw it's low rank in survey data. I told you about it being low rank in medicine. And you saw it being low rank in machine learning. We showed how to exploit low rank in order to fill in missing data, reduce the dimensionality of high-dimensional categorical variables, and automate machine learning. More generally, I think that low-rank structure is a really amazing method to turn big, messy data into small, clean data. So you can use machine learning methods. So you can use all the machine learning methods that you're familiar with and that are easy and fun, even on the most horrible data sets you've ever seen. Thank you.
This is great. Thank you so much.